All right, everybody, can you guys see me and hear me and see my slides? Awesome, wonderful, thank you. Okay, welcome, happy Friday. Welcome to our second to last class together. Today we're gonna finish up the chapter 10, which is our very last chapter together. So at the end of today, you will have all of the information from Chem 301 and hopefully be well poised to take Chem 302 in the spring or in the fall. Wow, it's the spring now. A couple of quick announcements for you guys. I am going to have some kind of pop-up office hours today. I will be available at the Zoom link from 2:30 to 3:30. I will also be in my office, so if you want to stop by, you're welcome to. A couple of other reminders and announcements over here on the left hand of the slide. Hopefully you guys saw that I did post an Achieve assignment. It's pretty short. I have it due at the end of the day on Tuesday of next week to be in sync with the very last day of classes, because I want you guys to have gone through the chapter 10 material before the reading day, before final exams start. I don't want this hanging over you into final exam period. Also, same thing with the quiz on chapter 10. As I've said before, it will be open book and it will be a take-home quiz. You guys can go in and out of it as many times as you want. You can use all of the resources that you have at your disposal. My sincere hope is that you guys will use this to your advantage and use it as a grade boosting opportunity. My recommendation is that you guys still try to initially treat it like a quiz. Set a time limit for yourself and try to answer all of the questions without looking at reference material after having studied. And then before you hit submit, go back and check your answers against the resources, against the textbook or against my slides, and make sure that your answers are all correct, because you have that opportunity with this quiz. So like I said, it'll be open book and take home. It will not have a time limit. Except in that it is due at 11:59 p.m. on the last day of classes. As you guys probably know, your final exam is Friday, May 6th. That is 1 week from today, 1 week from right now, actually. And I am going to treat this like a final exam and force it to stay into the final exam window that is set by the registrar. Sorry, someone asked in the chat box about the quiz, whether or not it has unlimited attempts. It does have, you'll be able to enter the quiz an unlimited amount of time, but you will not be able to submit it and then go back in and submit a second time. So once you hit the submit button at the end, it is submitted, but you can go in and out of it as many times as you want prior to that moment. Does that make sense? Okay, so for the final exam, it is going to be multiple choice only. It is going to be just like the part one of the exams that you've had, but it will have more questions than the part ones that you have done. It will be online and it will require the Respondus lockdown browser, but it will be multiple choice only, with the exception of there may be some kind of short answer question where I ask you state whether this or this is more likely and explain your answer. So there may be one or two questions where you have to write a sentence or write a couple of lines to show me that you understand really what's going on and that you're not just guessing at the answer. The final is not going to be the ACS exam. I am not giving the ACS exam. I write my own finals for this course the same way I've written all of the exams for this course along the way. So if you're studying based on the exams and quizzes you guys have taken and you're feeling good about the material on those, I think you'll be in good shape for the final exam as well. Okay, we'll talk more about the exam on Monday. And on Monday, we'll also kind of try to do a semester overview or semester review of everything we've covered, because we've covered a lot together. But today we have to cover some more material. So I want to really make sure we get to that today. So I'm going to go ahead and jump into the synthesis of alcohol. So here we go. We've been through most of the chapter 10 and we did a good amount of introducing you guys to organometallic reagents on Wednesday. Today I have some more final thoughts to say about organometallics. I'll extend the reactivity that I've introduced you to already to kind of a next level set of reactivity with organometallics. And then in the last little bit of class, we'll switch over and learn about ways that we can reduce a carbonyl compound to go from a carbon-oxygen double bond to a carbon-oxygen single bond. That's another method for synthesizing alcohols. So back to organometallics, I'm going to spend a couple of slides just refreshing everybody's memories since Wednesday. What we're doing when we're using our organometallic reagents is that we are trying to get a carbon atom to act like a nucleophile. And that's typically unusual. Typically, carbon atoms are more electrophilic, as in the cases of alkyl halides or the carbons of a carbonyl group. But by applying these organometallic reagents, we can create a situation where our carbon atom becomes essentially negatively charged, or at least it's carrying a large negative charge buildup, and that allows it to act as a nucleophile. And this is a really powerful tool for forming carbon-carbon bonds in organic chemistry. The reason that we're learning about this now is because if we take our organometallic reagents and react them with a carbonyl, the end result is going to be an alcohol after we protonate. And so that's why this whole organometallic section is in this chapter about alcohol synthesis. It's not just for alcohol synthesis. As I mentioned, it'll work for other things as well. But the key feature for this chapter is the reaction of these organometallic reagents, with carbonyl compounds. So what does this look like? This is the super generic, as top as you can, top level view of what we're talking about here. We can take an alkyl halide and we can create our own organometallic reagent by reacting it with a metal, like a metal 0, and turn that Rx into essentially an R minus, something that behaves as if that carbon is a carbanion. And that nucleophilic carbanion will react with an electrophile to form a new carbon to electrophile bond. And a lot of times these electrophiles can be carbon-based. And so that's what makes this a good carbon-carbon bond forming scenario here. And just to kind of reiterate that with words, we're going to start with an alkyl halide. We're going to make an organometallic reagent, either a Grignard reagent, R magnesium X, or an organolithium reagent, R lithium, which will make this carbon a nucleophilic carbon. And then we can react that with an electrophile to make a new carbon-carbon bond. Okay, so I showed you this slide on Wednesday also. This is an electrostatic potential map that hopefully helps drive the point home that one of the really powerful things about what we're doing here is that we are changing the nature of this carbon atom. When this carbon atom in iodomethane or any alkyl halide is part of an alkyl halide, the bond polarity dictates that that carbon will be delta positive because of the pull and the draw of the electronegative element pulling those electron density towards itself. So in a regular alkyl halide, our carbon is delta positive. But if we react it with magnesium 0 or lithium 0 and create our organometallic reagent, in this case, I'm showing you the Grignard reagent reacting with magnesium, that magnesium inserts into that carbon halogen bond and making this carbon metal bond. And that carbon metal bond has the opposite polarity than a carbon halogen bond because the metal is so electropositive that it's actually pushing electron density away from itself, the same way that over here the iodine was pulling electron density towards itself and away from the carbon. Our magnesium is pushing electron density away from itself and towards the carbon. And so that creates this negative charge buildup on the carbon atom, and it changes the reactivity of that carbon atom where it was electrophilic in the alkyl halide version, and now it is nucleophilic in the organometallic version. And again, it's going to act just like it was a C minus. You just have to know that it's not actually a C minus running around loose in solution. Okay, so we learned about two different ways to do this. Grignard reagents, which take advantage of magnesium, and organolithium, which use lithium to do the same thing. For the Grignard reagents, magnesium is in the second column of the periodic table, so it is ready and willing to give up 2 electrons, which means you only need 1 atom of magnesium to take care of every atom, every molecule of alkyl chloride. You generate 2 new sigma bonds on either side of magnesium using the 2 electrons that magnesium is going to give up and the 2 electrons that were in your alkyl halide sigma bond. Again, this is going to react like R minus. And here's an example. If we take bromobenzene and react it with magnesium 0, we can get this magnesium bromide Grignard reagent where the carbon with the red dot here that's right under my laser pointer acts as a carbanion. So I want to pause here and think about this for just a second, because this carbon is really the hydrogen on this, what would have been this carbon would have been not very acidic at all, right? So if we wanted to generate a carbanion right here where my laser pointer is by deprotonating benzene, that would have been really tough to do. It would have been really, really hard to do because the pKa of a CH2 of an sp2 hybridized carbon is very high. It's up in the 40s at least. And so this way of creating a Grignard reagent gives us that reactivity of a C minus without having to do a very difficult deprotonation. Now, the other thing to keep in mind about a deprotonation is that if you could find a base strong enough to do that deprotonation, it would deprotonate like everything, right? So in the case of benzene, it wouldn't matter because all 6 hydrogen atoms would be the same. But what if you had a substituent in one spot and you wanted to deprotonate just one specific location on that benzene? It would be really difficult to do. But with organometallics, it's not that bad because you just have to make sure you're organized enough to have your halogen at the place where you want to do the carbanion chemistry. And that gets selectively created into essentially carbanion. Okay, so just like magnesium can create organometallic reagents, lithium can also. In this case, lithium is in the first column of the periodic table. So what we have is each lithium atom only wanting to give up 1 electron. So we're going to need 2 overall equivalents of lithium to be able to generate both an R minus and an X minus, right? We need to add 2 electrons into the system to get this scenario here where we have broken apart our alkyl halide and made both sides of it an anion. We have a lithium chloride or a lithium halide salt and our organolithium reagent, which reacts as if it is a C minus lithium plus. And of course, all of this is very similar to Grignard reagents. The only real difference is that Grignard reagents require ether. Lithium reagents have a little bit more broad solvent capabilities. Still can't use an alcohol solvent, but you can use an ether or you can use a hydrocarbon solvent. And you can do this for either set, for the Grignard reagents or the organolithium reagents. You can do it on any alkyl halide, This works really well. As long as it's not an alkyl fluoride. So it works better with chlorides, bromides, and iodides. The fluorides don't work very well for this, but that's kind of a subtlety, so don't worry about that. My point is you can do it with a primary, a secondary, a tertiary, a allylic, an aromatic, a vinyl. It doesn't matter what the substituent pattern is. You can create an organometallic reagent out of any chloride, bromide, or iodide. Okay. Once you have that organometallic reagent created, remember our whole point here is to be able to make alcohols. So that organometallic acts as a nucleophile and we can react it with a carbonyl, which again has this polarity associated with it that makes the carbon at the base of the carbonyl electrophilic due to the polarity of the CO double bond and also the resonance structure you can draw for this carbonyl. What we get out is a new carbon-carbon bond, and the pi electrons that were part of our double bond end up being now a lone pair on our oxygen so that we don't break the octet rule for the carbon or anything else. Once we get here, we stop here. We just pause here until we provide a proton to quench our anion. And so this quenching that I'm talking about absolutely has to happen in 2 separate steps. The first step, we have our carbanion nucleophile, that's our R minus, part of our organometallic reagent, nucleophilically attacking at this electrophilic carbon, creating our new carbon-carbon single bond, and also turning our carbon-oxygen double bond into a carbon-oxygen single bond. In a second separate step, we provide a proton source to protonate our O minus, And we have to do this in a second step because any proton source that we would add here, such as water or H3O plus, or even just a generic H plus, any of those proton sources would react with our original organometallic reagent more quickly than anything else would. And so if we don't create this as a second step, a completely second separate step, then we would actually just kill our organometallic reagent. And so it has to be a separate, distinct step. So I'm going to go into detail about that a little bit more. What I'm saying is that these Grignard reagents are, we've talked about how they're exceptional nucleophiles. They're very good nucleophiles, but they are also incredible bases. And we just talked about how the pKa of an sp2 hybridized carbon is really high, right? So the hydrocarbons in general tend to have very high pKa's. What that means is that if you put this carbanion is essentially, this organometallic reagent is essentially a carbanion, which means that it's ready to get protonated because the conjugate acid of this base is something with an incredibly high pKa. That makes sense? So if you put an organometallic reagent in with water at the same time, that'll be the fastest reaction. You won't see any nucleophilic addition because all of your organometallic reagent will just get quenched and it'll lose its capability to react. So you can see that in these examples here. This is butyl lithium. So if you think about what the pKa of butane is, the pKa of butane is huge. It's above 45. So that means that butyl lithium is actually a strong enough base to deprotonate even something like this diethylamine, which has a pKa all the way up around 40. And so what you get is your butane and your deprotonated amine. It turns out there's an error in the slide and it had an extra CH there. That's your book's error, and it was just easier for me to correct it by crossing it out. But this, overall, what we're talking about here is that this carbon is acting as an anion. And so the most likely scenario here is that this NH proton is acidic enough, or I guess I should say this carbon is basic enough to deprotonate that amine. Likewise, you can use butyl lithium to deprotonate a terminal acetylene, right? The pKa of acetylene is 25. And if you have butyl lithium, it's a much, much, much stronger base than really anything out there. It's one of the strongest bases out there. It can deprotonate your terminal alkyne the same way we were using sodium amide to do this. We now have another reagent that we can use to do this deprotonation. Okay, the other thing that can happen that we need to be aware of and can be considered a limitation of these organometallic reagents is that if, just like if you have a carbon-oxygen double bond, really any time you have a multiple bond that has an electronegative element on one end, the organometallic can act as a nucleophile with any of these. So just like with a carbonyl compound, it can attack the carbon of a nitrile or any of these different functional groups that have pi bonds where one of the atoms of the pi bond is strongly electronegative. And so this is kind of a more advanced level, more subtle topic here that I'm talking about, but it's something to be aware of that if you want to practically, in a practical sense, if you want to use an organometallic reagent, you have to take a moment and make sure that there's not anything else in your substrate that would cause a problem for the organometallic reagent reacting where you want and in the way that you want, and that it won't go do side reactivity somewhere. And that's going to be a common theme that we have with any time we have a reagent that is very highly reactive like these. We have to pay attention to what else could it react with besides what we actually want it to react with. Okay, so at the end of last class, we talked about using this kind of approach, an organometallic reagent, in order to synthetically design a route to get primary alcohols. So I introduced this molecule here, formaldehyde, to you guys as a synthetic tool. If our target molecule has a primary alcohol in it, one way that we could get to this target is to react an organometallic reagent with this molecule here, formaldehyde, because it has all the pieces we need, right? It's a carbon-oxygen double bond. And so if we react our organometallic reagent with the formaldehyde, we'll create this new carbon-carbon bond. We have two CH bonds here from our original carbonyl that are going to be kind of our spectator bonds. They just go with the flow, right? And so those two CH bonds, which are just spectating and going with the flow, then become the substituents on the carbon holding the oxygen, right? And so we've generated a primary alcohol. And I asked you guys at the end of class to think about how you might use the same kind of strategy. What would you do if you wanted to make a secondary alcohol? So in a secondary alcohol, the carbon holding your oxygen is going to be attached to two other carbons, right? So think about that for a second. And if you thought about this over the last couple of days, like I asked you to, you can put your answer in the chat box. What kind of reagent or substrate would we want to use with our organometallic if we wanted to get a secondary alcohol? You guys have any guesses? I find it easiest to think about that from here. So we're talking about needing to make a scenario where our alkoxide has only one CH bond, and then it'll have two carbon-carbon bonds. One of those carbon-carbon bonds will have come from our organometallic reagent, but the other carbon-carbon bond would have come from our carbonyl. So any guesses before I show you? A chain with a ketone in the middle. Close. Keep thinking in that same idea, but note that what we want is a synthetic piece that looks kind of like this, which looked like this before it did the reaction. We want a CH bond still because we want it to be a secondary alcohol at the end, but we want a carbon-carbon bond on the other side. So in order to do that, what we can do is provide our Grignard reagent with an aldehyde. So if we provide our Grignard reagent with an aldehyde, then we have on our carbonyl compound a CC bond and a CH bond. Those are shown here as spectators moving forward. And we're going to add in another CC bond when we introduce our Grignard reagent here. And so the end result of this will be a secondary alcohol after we protonate it, where one of our CC bonds came from our carbonyl, the other CC bond came from our Grignard reagent. Okay, now what do we do if we want to make a tertiary alcohol? If we want to make a tertiary alcohol where all three of these carbon substituent bonds are carbons, what do we do now, John? Now we use John's ketone. And now if we react our Grignard reagent with a ketone, and our ketone doesn't have to have the same carbon-carbon bonds, they can be substituted with different carbon-carbon bonds, right? If we take our Grignard reagent and we react it with a ketone, then we have an access route to tertiary alcohols, where one of our carbon-carbon bonds came from our Grignard reagent, and the other two carbon-carbon bonds came from the ketone. Okay, so everything that you're looking at on this slide here is the same reaction, right? It is the same reaction, it's the same mechanism, but I've broken it down in this way so that we can start thinking about things in terms of their synthetic utility. So what do I mean by that? Well, if I tell you to make this target compound and you see that that target compound has a secondary alcohol in it, you can think to yourself, oh, well, that alcohol could have come from a carbonyl. And if I bring that alcohol backwards to a carbonyl, one of these three bonds could have come from a Grignard reagent. And then you're just left to decide which of those three bonds would have come from the Grignard reagent. Okay, so formaldehyde gets us to primary alcohols. Aldehyde gets us to secondary alcohols. Ketones gets us to tertiary alcohols. With that in mind, take a moment. We're going to do this sample problem together. You don't have to turn this in or upload it. We're going to do it together, but I want everyone to take a moment and look at this compound and think to yourself, how could I synthesize this compound? Starting with compounds that have no more than 5 carbon atoms. That's your restriction here. Everybody take 1 minute to think about that, and then we'll talk through an answer together. Okay, I'm gonna give everybody another minute, but if you're stuck and trying to figure this out, think about how this is a tertiary alcohol. It's a tertiary alcohol, so we can build a situation where one of these carbon-carbon bonds came from a Grignard reagent and the other two of the carbon-carbon bonds came from a ketone. I'm gonna give everybody another 30 seconds to kind of wrap up your thoughts, then we'll go through this together. Okay, so let's pause and take a look at what we think this might look like. If indeed we're going to break down this compound to come from a ketone and a Grignard reagent, there are in fact 3 different ways that we can do this. Only one of the ways satisfies this stipulation that's written into the question about not having more than 5 carbon atoms in a reagent, but there are indeed 3 different ways to do this. So one of these carbon-carbon bonds should come from a Grignard reagent. The other 2 alkyl groups should come from a ketone. So there's 3 different combinations. We could start with a ketone that has the cyclopentyl group and the methyl group and provide it with an ethyl Grignard. Or we could start with a ketone that has the cyclopentyl group and the ethyl group, provide it with a methyl Grignard. However, both of these situations have one of our substrates has at least 7, if not 8 carbons. So those 2 are no good. The only one that fits the bill for the actual question asked is to take our ketone and put both of our alkyl substituents, our linear substituents, on the ketone. So we have a ketone that's substituted with a methyl group on one side and an ethyl group on the other. And then we can use our Grignard reagent to create our cyclopentyl group, which would look like this. Now, if you wanted to, you could have taken this a step further back and you could have said, well, I'm going to start with cyclopentyl bromide and add magnesium 0 to make this Grignard. But because I only told you had to use things that have no more than 5 carbon atoms, you can go right to this Grignard. Now notice in every single case here, we are doing a 2-step process. The first step is our Grignard reagent interacting with our electrophile. And then in a completely separate second step, we're providing a proton source to get to our alcohol product. Okay, so this is a really good problem for starting to see how useful it is to think backwards about how to disassemble a molecule that you want to make. This is called retrosynthetic analysis, and it's a common way for chemists to think. Chemists actually, it's like a logic puzzle, right? You work with whatever you have. You start at the beginning and look forward, and at the same time, you're looking at the end and looking backwards until you find a set of a pathway that is functional kind of in both directions, meets in the middle. Okay. All right, so we have been talking about these organometallic reagents and their reactions with aldehydes and ketones, bringing us to these alkoxides. Turns out there's a whole kind of subclass of a sort of a next level version of this with specialized carbonyl compounds that I want to introduce you guys to that can be really powerful. So in the case of aldehydes and ketones, we do this reaction to the alkoxide, and then the reaction stops. It gets to this point of this O-, and it just waits there and does nothing until we provide it with a proton, right? It turns out that is because once you get here, none of these 3 bonds are going to be likely to be broken. Now, how could you break one of those bonds? Well, you can actually imagine a scenario where the lone pair on the oxygen comes back in to form a new carbon-oxygen double bond, which of course would overly saturate the carbon with electrons. So it would want to break one of these 3 bonds and push out one of those groups with the electrons. So if one of these 3 groups were a good leaving group, you can actually reform a double bond and push out one of these three groups. Now, like I said, in the case of aldehydes and ketones, all three of these groups are going to be carbon-carbon bond or carbon-hydrogen bond. And hydrogen and carbon are not ever going to be happy to leave with a pair of electrons. Their pKa's of the conjugate acids of these leaving groups would be too high, and so they will never be leaving groups. What I'm talking about here is if this hydrogen atom left with electrons. That's not likely at all. But if you think back to chapter 2, you guys learned about all sorts of different functional groups with carbonyls. And I've been talking about carbonyl reactivity here, kind of glossing over the fact that there's a whole bunch of other carbonyls besides aldehydes and ketones, right? So we need to address that now and take a look at what happens with those other carbonyls. So here is a chart showing a lot of different carbonyls. Many of these you guys learned about in chapter 2, like carboxylic acids and amides and esters. I don't think you learned about anhydrides, but an anhydride looks like this, where one side of it is essentially what looks like a carboxylic acid. And then I think you learned about acid chlorides or acid halides as carboxylic acid derivatives. All of these things above this black and white dotted line are considered carboxylic acid derivatives. You can see how much they look like a carboxylic acid. But they have specialized reactivity because each one of these cases, you have, as you kind of head up this chart, an increasing propensity for that group, whatever that group is attached to the carbonyl, to be able to manage leaving with 2 electrons. So notice the left-hand side of all of these molecules is identical, right? We're talking about a carbonyl attached to a carbon-carbon bond on one side and then something else on the other side. And the question is, what is that something else? And what does it do to the reactivity of these compounds? All right, so if we are going to react a carbonyl and a Grignard together, we're going to get to this intermediate, right? This alkoxide intermediate, which is going to be a tetrahedral intermediate, right? It's carbon bonded to 4 things. So even though I keep drawing it out as if it's flat, it is actually a tetrahedral intermediate. In the case of aldehydes and ketones, this is where you stop, right? Anytime you cannot have a leaving group, this is where you stop and it'll just hang out here and wait until you provide it with a proton. If, however, any one of these 3 bonds is to a good leaving group, then you can reform your carbonyl and push that leaving group out of the equation. And what you'll be left with is another carbonyl that can undergo a second addition of an organometallic reagent. So we'll go through this step by step, but to give you kind of the bird's eye look at this, what I'm talking about here is if instead of R group, a carbon or hydrogen, you had a Y group where it's not carbon or hydrogen, but is instead a good leaving group, like an OR minus, or this carboxylate group, or this chloride. These are all good leaving groups because the pKa of the conjugate acid is low enough that they're considered to be stable carrying around that negative charge. So if you have a leaving group here, then what can happen is that the lone pair of electrons that you just put up there on that oxygen can come back in, create a new carbon-oxygen double bond, and in doing so, you would have to lose 2 electrons from the carbon to make it not break the octet rule. So those 2 electrons would leave with the leaving group. And so when you do that, like I said, you're reforming your carbonyl, and that makes your intermediate here susceptible to a second attack by a second equivalent of a Grignard reagent. I'll show you some mechanistic slides, not on this slide, but on the next one. This slide is giving you the overview look at what happens. When you react a Grignard reagent with an acid chloride or an ester, what happens is that you end up incorporating 2 equivalents of your Grignard reagent. And what you get in the end result is a tertiary alcohol where 2 of the groups are identical because 2 of the groups came from that Grignard reagent. And I'll go through this mechanistically on the next couple of slides in a way that I think will really clarify it. But what I'm saying here is that we're going to have 1 Grignard do an addition into this acid chloride to create a tetrahedral intermediate, but then that tetrahedral intermediate will collapse and kick out a chloride, reforming a carbonyl that will be susceptible to a second attack by a second equivalent of Grignard. So when that happens, what you get is two equivalents of Grignard forming two new carbon-carbon bonds that are identical to each other. The remaining carbon-carbon bond came from your carbonyl compound. And then, of course, you have this OH where your double bond carbon-oxygen has now become a single bond carbon-oxygen. So what that looks like is a tertiary alcohol. And this is true whether you use an acid chloride or an ester to do this. Okay. Someone's asked, is there a possible steric hindrance involved with an organometallic or Grignard reagent attacking a secondary carbon, especially with bigger groups? That is a great question, but the answer is actually no. Because if you think about what your carbonyl looks like, this carbon is sp2 hybridized. So all of these atoms are in a plane. And so it actually makes it so the nucleophile is attacking from a direction that there's nothing sticking out in that direction because all of the atoms are planar. Okay, so mechanistically, here's what this looks like. This is the acid chloride version. We can take our Grignard reagent, nucleophilically attack at the carbonyl carbon, which is an electrophile, to create our intermediate. This step looks exactly the same as what we've been talking about for aldehydes and ketones. In an aldehyde or ketone, you couldn't go any farther. You would be stuck here. But in the case of an acid chloride, this chloride is a really good leaving group. So that lone pair will come back in, reform a double bond, and push out the chloride, getting us to a ketone intermediate. This ketone intermediate is a ketone, and therefore it's a carbonyl, and therefore it can be susceptible to attack by another equivalent of Grignard. So here's the ketone, the same one we created in our kind of first Grignard addition sequence. In our second, we're going to take another second equivalent of a Grignard and do the same thing now with this ketone. Now we're going to get stuck at this alkoxide. This alkoxide can't do anything else until we provide a proton in a separate step. So once you get this process started, there's no way to stop at any of these intermediates, right? Until you get to the last one. So all of this is happening all at the same time in a pot together until all of your material funnels to this position here. And then it just waits here until you provide a proton. All right, esters look exactly the same as this. In an ester, you just have a slightly different leaving group. But a Grignard attacks at a nucleophilically attacks at the carbon of a carbonyl. You form this tetrahedral intermediate. And then because OR minus is a good leaving group, this oxygen lone pair can reform your carbonyl, kick out your OR minus with those two electrons, and form a ketone where one of these carbon-carbon bonds came from our original ester. The other carbon-carbon bond came from our Grignard. That ketone, same as before, the bottom half of this is identical to the last slide. Now you have a ketone, so the second equivalent of Grignard will also attack the ketone, and it'll create this alkoxide intermediate where now two of our carbon-carbon bonds came from our Grignard, one carbon-carbon bond came all the way back from our ester, and it'll stop here until you provide it with a proton. Okay, so one more thing that I want to tell you about organometallic reagents, and that is that, and I should say, let me move back just one slide. I keep showing these with Grignard reagents because I think that Grignard reagents are more common. They're also a little weirder to look at, so they might be more distinctive. But anything I'm telling you about Grignard reagents, you can do with organolithium reagents too. They're identical in their reactivity. So on that note, let's see one more type of reactivity that organometallic reagents can do, and that is that they can attack epoxides. So again, this is a chapter about synthesizing alcohols, and epoxides can be precursors to alcohols. So if you take a Grignard reagent and you react it with ethylene oxide, which is the simplest 2-carbon version of an epoxide, what you get because of the ring strain in the epoxide is an SN2 nucleophilic substitution reaction where your Grignard reagent acts as a nucleophile, breaking this carbon-oxygen bond. That oxygen acts as a leaving group. And what you've gotten as an end result here is an addition of CH2, CH2O. So we've taken an alkyl group and we've extended the chain by 2 carbons and an oxygen. And so this is actually a very synthetically useful reaction also, if what you need to do is add in 2 carbons and an oxygen. This is just an example that's not a generic example, but one with real actual molecules. And that is that we can take butyl magnesium bromide and open up this epoxide. And what we're doing here is it's a butyl magnesium bromide, so it has 4 carbons. And now our end result product has 4, 5, 6 carbons plus an oxygen. So we actually just took butyl magnesium bromide and we made hexanol. It's kind of neat. So we can actually take butyl bromide, introduce magnesium to make our Grignard reagent, introduce ethylene oxide, and we can go from butyl bromide to hexanol through this sequence. And so you can start to see how you can pull all of these different reactions from these different chapters and different sources to start synthesizing molecules. And the more reactions you know, the bigger your toolbox is, the more complex you can get with the syntheses you're trying to do. Okay. So one more thing I want to mention about organometallics before we move on to reduction of carbonyls for the last bit of class is that I talked before, this slide should look familiar because it's the same slide as earlier in the lecture today. But I talked about the limitation of how these Grignard reagents and organolithiums are also strong bases. And so we have to watch out for that. We have to make sure that we don't introduce any acidic protons into the mix when we're using these organometallic reagents. But what that also means is that we can harness this and use it for something functional. So say we have a alkyl halide and we don't want that halogen there anymore. We want to replace a CX bond with a CH bond. This provides us with a very convenient and very kind of safe way to do that, where we can take an alkyl halide, we can turn it into a Grignard reagent, right? So if we have an alkyl halide, we can turn it into a Grignard reagent, and then we can just take that Grignard reagent and dump it in some water. And what we've done overall is taken our RX, our alkyl halide, and turned that bond into an RH bond, right? So that can be actually synthetically useful. And your book talks about ways to use this to our advantage in section 1010. So what could be a tragic kind of difficult reactivity to pay attention to can also be useful in some cases if we know how to use it. Okay, that's the end of organometallics. I'm going to take the last couple of minutes of class to introduce you guys to the reduction of carbonyls. I think I might be able to finish carbonyls, reduction of carbonyls, but if I don't, we'll just, tie up these loose ends on Monday. Someone asked if this organometallic, this last slide here, is a good method to prepare alkanes. It can be, depending on your situation. So yes, you're making an alkane here, but it's not usually a synthetically useful route to alkanes because you have to have the halogen there in the first place. And so most of the time, the effort that you would go to put the halogen in place is, kind of roundabout. It's more useful if you have a halogen already that you don't want. But yeah, in general, yeah, it's a way to make alkanes, yes. Okay, for the reduction of carbonyls, what I'm going to talk about today for the reduction of carbonyls is hydride reagents. So these hydride reagents are going to be a source of H-. This will actually be H- in quotes, the same way that our organometallic reagents are C- in quotes. So this hydride ion, again, is a hydrogen atom carrying 2 electrons, so it's carrying a negative charge. And this hydride atom can reduce a carbonyl group to take our CO double bond to become a CO single bond. And I'll show you how that works in the slides coming up. But just a reminder that this idea of reducing, a reduction involves a gain of electrons. So our carbonyl group is getting reduced, which means it's gaining electrons, and those electrons that it's gaining are coming from this hydride reagent. Okay, if we have an aldehyde and we reduce it, we're going to get a primary alcohol. If we have a ketone and reduce it, we're going to get a secondary alcohol. And we'll see some examples of this. But first, I want to introduce the reagents to you guys. These are the two reagents that you'll need to know about reduction to carbonyl. They both work mechanistically in a similar way, but they have different capabilities. Sodium borohydride is more weak, and it'll only react with a subset of carbonyls. Lithium aluminum hydride is a stronger reducing agent, and it'll react with pretty much all carbonyls it comes in contact with. And I'll show you that in the next couple of slides. These are called complex hydrides because the hydrides are bonded in this complex ion fashion. They're not simple ionic relationships like a sodium hydride or a lithium hydride. These two, sodium hydride and lithium hydride, the simple hydrides are strongly basic and strongly nucleophilic, but in complex hydrides, because you're bonded in this complex way, the hydride can act as a nucleophile, but it is shielded from acting as a base. It is essentially kind of stabilized by its interactions with the boron or the aluminum. And so it does not act as a base, but it can act as a nucleophile. And so we'll see how that works in the slides coming up. All right, this should look familiar. It should feel familiar. This is how this works. We have a hydride ion acting as a nucleophile, and we're reacting it with a carbonyl. So that carbon of the carbonyl is an electrophile. So here we are delivering a hydride to this carbonyl. We've made a new carbon-hydrogen bond, and of course, because of the octet rule, we're moving our pi electrons up to the oxygen. So this is the reduction part. We just reduced this carbonyl because we gave it more electrons. We gave it the electrons that came in on this hydride. As you might suspect, we have not formed an alcohol just yet, but we are real close. In a separate step, we are going to quench our alkoxide ion with a proton source. So this should feel familiar to you guys also. So I told you there are two different reagents to do this. Sodium borohydride is the weaker or more mild reagent. And that might sound like a bad thing, but it also could be a good thing because it means that it can be selective. So sodium borohydride will only react with aldehydes or ketones. It will not react with any of the other carbonyl reagents that we saw on that big chart. Only aldehydes and ketones. And it's selective, so that means you can do this reduction even when there's a different carbonyl compound around or a different carbonyl functional group in your same molecule. So if you have an aldehyde, then what you're getting is hydride addition at the base of the aldehyde, followed by protonation up here. So you're essentially adding H2 across a CO double bond. It's like a hydrogenation of a carbonyl. It's just not using molecular hydrogen and not going by the hydrogenation mechanism. It's going by addition of H minus, followed by addition of H plus. And so you can turn this aldehyde into a primary alcohol, or you can turn a ketone into a secondary alcohol. And so this is sodium borohydride. It is the weaker of the two. I will pick up here on Monday. I'm going to post all of the slides about reduction of carbonyl so you guys can see what's coming. But I will finish up. We only have 3 more slides, but I'll finish those last 3 slides on Monday because of the time. And someone asked in the chat box, do we get extra points for filling the evaluation? No, you do not get extra points for filling the evaluation, but I do appreciate your feedback. And so I would love it if you would fill out that evaluation. But I don't have a way to know who has filled it out and who hasn't because it is anonymous. And so I don't have a way to track that. And so no, you do not get extra credit for filling out the evaluation. But I do think I've provided you guys with a lot of extra credit opportunities throughout the semester. And I'll try to remind you of those as we come into our last day of class on Monday. And then someone has also asked, where do we turn in the Earth Day extra credit? There should be a space now for you guys to turn that in under the assignments tab in Canvas. If you cannot find it, Kelly, will you please send me an email? I'm going to designate you to check on that and send me an email, but it should be under the assignments tab. And I want everybody to be aware of this because there's instructions for what the write-up needs to include in order to get full extra credit. So make sure you read the instructions before you turn in your summary of the webinar for Earth Day. All right, any other questions?
I have a quick question. For homework assignments that are late, when do we have until to turn those in?
That's a good question. I have to look at a calendar to answer that question, but I'll let you know on Monday. Is that okay? It won't be until after your exam.
Okay, perfect. That's what I wanted to know. Thank you.
Yeah, you're welcome. And someone else has asked, when will exam 3 grades be out? So the Canvas online part 1 grades are almost ready to go, and I can release those today so you guys can look at your scores for part 1 and you can look at your questions and answers for part 1. I can also post the answer key for part 2 today, but the part 2 grading will probably not be done until Monday is my guess. But I will give you guys as much as I can right now, and then on Monday you'll be able to see the full total grade breakdown. Okay, guys, if there are no other questions, then thank you very much, and I will see you guys for our very last class together on Monday.